Hey PTs, Craig here again with another lecture from the AMP series. This one is on joints of the human body. In this lesson we're going to be discussing a few different things to do with joints. We have obviously joint types that we find in the body, the structure of the pieces found within the joints. We'll look at factors that affect range of movement within a joint and also factors affecting stability. So we'll start with joint names and how joint names are derived. The technical joint names we're talking about here, obviously you guys are familiar with things like shoulders and knees and ankles, but from a technical standpoint these have a secondary name. You can see a few on the screen there, and it's pretty easy to work out why they're called what they're called. If we look at the sternoclavicular joint, that is the meeting between the two bones of the sternum and the clavicle, right up the top of the torso. And you can see that the name is derived from the two bones that are found within the joint. The atlanto-occipital joint may not be quite as familiar to you guys. The occipital bone is or occipital protuberance is the bump at the base of your skull at the back of your head, and that coincides or co-joins with the first of your cervical spinal bones, and of course that one's called the atlas bone. So you've got the atlanto-occipital joint, which is effectively a hinge joint that makes you go yes. So it's the one where nodding your head is originating from. And then the last one on the list there is the humeroscapular joint, where obviously the humerus meets the scapula. You'll better know that one as the shoulder. Joints are also classified by type, depending on the structure of the joint generally. The structure will depend on how the two bones are joined together, what substances effectively co-join the bones within the joint. So there are a few different types we're going to work through. You can see there on screen: fibrous joints, cartilaginous joints, synostosis joints, and synovial joints, the major movement joints of the body, which we'll spend most of our focus on. So let's dive in and have a look at fibrous joints. So fibrous joints are effectively joints where bone plates or bone parts are held together by collagen fibers, and those collagen fibers effectively emerge from the periosteum or outside casing of bone, and of course connect into the periosteum of another bone. So it's a very strong connection. There's essentially no joint cavity there, which means there's no space between the two bones and therefore no fluid filling that cavity. Examples of fibrous joints you can see there include skull sutures, so the picture we just looked at before, you can see the plates of the skull, and obviously that's there for the purpose of allowing those skull bones to continue to grow, to allow for brain growth as you age from infant through to adult. The collagen fibers allow that level of flexibility where we don't have to fuse the plates yet, we allow them to grow and continue to be connected, but retain that ability to expand. Teeth in their sockets is another example of a fibrous joint, so gomphosis that's known as, and you can see here a tooth in the socket. Down here you see the bottom edges of the tooth here, known as the roots. Okay, and we often think of the roots as the dangly bits that are hanging off the tooth when it falls out of a child's mouth, but in fact those are the periodontal ligaments that we see attached there, and that is of course collagen fibers that are attaching the bony root of the tooth here into the jaw bone. So collagen fibers there again, and again this gives it the ability for those two bones to be separated at some point, and when we need to grow our adult teeth. Obviously if we dissolve those collagen fibers and push through with the teeth coming in underneath, then you get you get the idea of the use of having removable bones in that sense. Later in life, not so fun when those fall out. Those collagen fibers can obviously erode and the teeth can decay and become detached that way, and of course you end up with holes in your teeth for life at that point. The other one on that list was simply the tibiofibular joints, which is where we hold together the tibia and fibula to keep them aligned in the lower leg there, and that just has a few collagen fibers holding those in place there. Also helps the bones keep aligned as well. You know, there's a gap between the tibia and fibula, and we fill them up with collagen fibers too to keep the two bones aligned and stop them sliding away from each other. Alright, the second one is cartilaginous joints. And pretty obvious what separates these two bones, and that's cartilage, one of the connective tissues within the body. So two bones bound by cartilage or cojoined with a separation of cartilage between, and we've got cartilaginous joints. There are two types of cartilage that we find in joints, that is hyaline cartilage and fibrocartilage. So hyaline cartilage is softer, often has a grey-blue tint to it, and a good way to think of hyaline cartilage would be the gristly flat that sits over the end of a chicken drumstick bone. Ribs to the sternum are a good example of hyaline cartilage and why we need this sort of flexible nature. Obviously ribs need to expand and contract during the breathing process, and if there was a bone-to-bone connection going on there, you wouldn't get the same type of expansion possible. And also give, if impact is received around the ribs, that allows for a certain element of give, meaning that we don't pop a rib or break a rib. Sorry, just move back there, got ahead of myself. Other places where we find hyaline cartilage are pretty much all main movement joints, so we're talking elbows and knees and ankles, etc. This hyaline cartilage would form a protective surface or protective layer over the ends of the bones and the joints, so that when compression occurs and the two bones come together and potentially would contact, you have a protecting surface there that allows those two bones to glide across each other rather than grate and cause inflammation or injury. In the event of this articular hyaline cartilage not being reproduced effectively or being worn away, then two bony surfaces would indeed rub, and that would cause inflammation in the joint that we know of as osteoarthritis. Fibrocartilage is a much tougher type of cartilage. Its chondrocytes or cartilage cells are packed much more closely together, and it's much closer to bone than the more soft and flexible hyaline cartilage. For that reason, you find it in places that we don't really want to separate at all. We certainly don't want these surfaces gliding past each other. The one that we see on the screen there is the pubis symphysis, which is the co-joining between the two bottom halves of the pubis on the pelvis here, so this guy here, and we certainly don't want that separating in most instances during human life. During pregnancy, however, we might see a degradation of this cartilage here to allow for the expansion of the pelvic rim there and allow a baby's head to make passage through the birth canal. Certainly any other time in life you'd want those two bits to stay together if possible. The other place where we want some tough cartilage is where the cartilage separates the bones of your vertebrae. We know about of these as intervertebral discs. Most people know there are discs in their spine between the two bones. We often hear about a slip disc, for example. These have to be pretty strong. They're essentially fluid or liquid-filled discs that compress during the day. They absorb force, and we wouldn't want them sort of bursting open and the inside coming out, something that's called a disc herniation. So they're pretty tough. They take a bit of a beating over our life cycle, but tend to do their job fairly well. So we have hyaline and fibrocartilage, the two types of cartilage separating cartilaginous joints. Next we look at synostosis joints, and the easiest way to explain a synostosis joint is that it is two parts of a bone or two bones that are in alignment that we don't want moving at all. So there may be a reason, and the reason I'll talk about very shortly, of why you would want to separate these two bones for a start and then have them fused later. But effectively, where you had a fibrous joint or you had a cartilaginous joint during the growth phases of your life, when you reached adulthood, these joints ossify and become one. Classic examples again are the bones of the skull. Once you reach physical maturity, there's no reason for those plates to move any further and expand with the brain, so they will fuse and form one entire bony casing that we know as the cranium. The shafts in the head of the long bones is another place where you see this in evidence. So if I pan back to this picture here, you can see that in the initial pictures here, we have a shaft, the diaphysis bone, and we have the ends, the epiphyses bone, and they are actually separate bones at this point. They are held together by an articular cartilage layer, and as we've explained in the bones segment in the skeletal system lecture, bone length continues to grow out of that hyaline cartilage sort of layer that's there. Once we reach full maturity, though, we certainly don't want the top of this popping off. So the growth plate, or epiphyseal plate as we know it as, fuses, and the bone becomes one. So one way of thinking of it is essentially, as you're growing, you have 3 bones for every long bone in your body. You have the 2 epiphyseal, or epiphyses here, sorry, the epiphyseal plate or growth plate separating them, and then you have the shaft making up 1, 2, 3 bones which fuse into one. And that's why you'll often hear that infants and children have well over 300 bones in their system, whereas an adult has 208. It's not that we lose any bones, simply that the bones fuse together when we hit that sort of skeletal system maturity around that 16 to 18 year mark. The other example on there was the first rib to the sternum. If I take you back to look at this picture of the rib cage up here, just bear with me. Realise we're zinging around. Hope you don't feel too sick. We determined that this was hyaline cartilage that was in between the ribs and the sternum here to allow that flexibility, but we actually need a rigid structure at the top, and the first rib to sternum is actually a synostosis joint, a bone-to-bone joint, and that's to provide an anchor for muscles in your neck that hold down that first rib as the rest of your ribs project upwards and outwards. If that didn't happen, of course, then the first rib would likely try to come up. And with the clavicle sitting over the top of it, you can see that wouldn't be a good thing to do, as the first rib comes up and simply pops the clavicle off the sternum. Wouldn't be a great idea, so that's why that is a synostosis joint. Okay, so we'll just pop onto the next part here, and that brings up synovial joints, and these are probably the crux of our studies because these are the main movement joints of the human body. You'll see there on the skeleton that there are some mechanical depictions of these types of joints. We can see the neck, we can see the elbow, the wrist and thumb. We've got the hip socket there, and of course we could talk about the shoulders and the ankles as well. Each of these can be classified into different types of synovial joint, which are classified by their structure, the shape of the 2 bones that are meeting there. Now, these are very relevant to us because these are obviously the ones that we are essentially utilizing most in an exercise situation. So when bones are separated by a slight joint cavity, which is a space between the 2 bones, we can fill that cavity with water, which gives a cushioning effect and also a lubrication element to the joint, which is really important when you're using it as much as we are. When you think about shoulders and hands and ankles and running and all those kind of things, we need that added cushioning, and we also need that constant gliding between those 2 bones to be supported by a fluid-filled sac that keeps things lubricated and stops friction occurring. Inside a synovial joint, we're going to find some different structures here. So we have synovial fluid, as I mentioned. We have articular cartilage, which is the cartilage protecting the bones in the joint. We have a fibrous joint capsule that emerges out of one periosteum of one bone, wraps across the entire joint, and then emerges into the periosteum of another bone. So if we look at it here, and this is obviously an interphalangeal joint here in the finger, a knuckle as we know it. Here you see one bone. You see the other bone that cojoins in this joint set up here, and here is the capsule that wraps itself from the periosteum of the top bone here across the knuckle joint and grows into the periosteum of the bottom one here. And what that allows it to do is form sort of a watertight capsule that the fluid can fill in these spaces here. So the black space you see there is effectively where the fluid would sit. The little black strip that's between the 2 bones here would be known as the cavity, and that means there's a little bit of space between the 2 bones. Really important for when it's loaded, that they're not touching at that point. And here we see a blue layer of articular cartilage, which is protecting the bone against the other bone when they do come under contact in loaded situations. The only other part or structure that's important, and these structures, it must be noted, are found in all of the synovial joints that we'll look at. The same principles apply. We have a joint capsule, 2 bones, the articular cartilage, and the cavity filled with fluid. We also have a synovial membrane, which is the inner wall of the capsule, and its function is to produce the lubricating synovial fluid and keep regenerating that, so we keep it nice and fluid within the joint capsule there. So, just to recap those structures, we have the synovial cavity, a space between the two bones. We have the membrane on the inside of the membrane or capsule, which produces the synovial fluid. We have the synovial fluid itself, which has lubricant characteristics. In fact, synovial fluid has more than just lubrication as its function. It is actually the way that we distribute nutrients within the joint. One thing you won't find within the joint capsule is blood. So it's kind of a blood-free environment. And given that blood is the major nutrient distributor within the human body, it's the thing that makes it into all other spaces in the body and delivers the oxygen, delivers the nutrients and fuels, and removes the waste. That puts the joint, I guess, at a bit of a disadvantage. And in some respects, that's why structures found within joints when injured are so slow to heal. When we talk about ligaments within that capsule, when we talk about cartilage and meniscus that we find within joints, they're often very slow healers because the blood flow to those areas are very limited. And blood brings with it a lot of healing properties. So instead, what happens here is blood vessels will effectively make their way to the joint capsule, where they can pass the nutrients and other goodies through the wall of the synovial membrane here, and then those nutrients are put into the synovial fluid. As long as we're then active and we are constantly squishing and placing pressure on the joint, those nutrients will make their way into this very small porous holes that we find in the articular cartilage, and that in effect regenerates the cartilage, keeps it healthy, and removes the waste. The waste can then be repassed through the wall of the membrane back to the bloodstream, and the process is repeated over and over to keep it healthy. The more active we are, the more healthy the joint generally is, provided we're not providing too much aggravation to the joint there, and we have a significant layer of articular cartilage there. Its other role is obviously shock absorption. We can see here at the bottom, if you have a fluid-filled sac, it's going to allow you some extra form of cushioning there. So here are some common synovial joints that we'll talk about in the body, and here are their common secondary classifications, if you like. So most people are aware that the shoulder and hip are known as ball and socket joints, given the ball-type nature of the top of one of those bones, such as, say, the humerus or femur, and then the socket that it then sits in against and is connected to in the joint. And that allows this ball and socket situation a vast array of movements. The shoulder is by far and away the largest movable joint in the body, meaning the range of motion we can achieve with it is second to none. The hip doesn't quite have the same maneuverability in most people. That's because the hip, being more of a loaded joint, taking and bearing the weight of the body, has a deeper socket with the ball sitting deeper inside it, and therefore limiting the amount of rotational movement that occurs in that joint. And the limit of hip rotation, hip flexion, hip extension, hip abduction, and those types of movement is really limited by bone-on-bone contact. So a bone will rotate through the joint until the head of that bone cracks against the bone of the socket. Okay, so it has a limited range of movement. And we all have different characteristics, so that allows for the differences between people who are very hyperflexible. They may have very shallow sockets versus people that are very inflexible and structurally have very deep sockets, which means that the head of that bone can't rotate far before it hits the wall of the socket. We then have the elbow, known as a hinge joint, primarily because it works only in one plane. We know that it flexes and extends and doesn't do much else. The atlas is also known as a hinge joint. That's the one we talked about before, the atlanto-axis joint, which is the hinge joint for yes, nodding. We have knees, which are primarily hinge joints, but are also viewed as potential condyloid joints, something we'll talk about soon. The ankle, again, a hinge joint, but also has gliding characteristics. Again, gliding is something we'll talk about very, very soon. And then we have other pivotal places in the body where we have a rotation-based joint. Axis, second joint in the neck would be that one where we do no, effectively shake our head. And then we have a standalone sort of bone, the thumb, which is known as a saddle joint for reasons I'll explain as we get back to here. So here we go. Classic ball and socket joint up the top here. You can see a ball sitting in a socket allowing multiple ranges of movement there, including flexion, extension, abduction, adduction, and most importantly rotation, which sets it apart from a lot of the other joints in the body. A pivot joint, like the second vertebrae in the neck, between C1 and C2, we can see a bone fitting inside a little circular opening in another bone, and this mechanical representation here, which means it can turn, and that of course turns your head from side to side. You also have a similar setup in the proximal radioulnar joint, where we produce the movements of pronation and supination. It's also known as a pivot joint. At the elbow, you see the hinge here, a shallow sort of groove with a cylindrical type ending to this bone here, which sits in it and allows it that degree of movement in one plane only, just like the hinge of a door. A condyloid joint is effectively a shallow ball and socket joint. So it allows many of the same movements as a ball and socket joint, except for one pivotal one that I mentioned before. So a finger is effectively a condyloid joint. If you think about it, a finger can flex and it can extend. So you can bunch your fingers and extend them out again. You can abduct your fingers, taking your fingers wide apart, and you can bring them close together, which is adduction. But one thing you can't do with a finger is rotate it. Okay, so you can't rotate a finger on its own. You can obviously rotate your wrist, but not your finger. And the shallow nature of the ball and socket joint is one of the primary reasons for that. The bone is not secure enough in its shallow socket to be able to rotate without, of course, falling out of the socket. We have plane or gliding joints. So these are referred to as gliding joints before. These are the short, bony masses of the tarsals in the feet and ankle, and of course the carpals up here in the wrist. And these are little boxy bones that sit next to each other, held together by ligaments, and they can move slightly in each direction. So they can go up, down, sideways, back and forward, but not very far because they're held by their ligament structures. And what that allows is a certain degree of maneuverability, where it allows us to get our hands into those positions where we can cup something or pick up a tennis ball off the floor and create that cupping sensation in our hand, or when we're walking over uneven surfaces, our foot gives, and when we hit a lump or a bump or a hole, we have that allowability of give, which helps us prevent injury and allows for that maneuverability when we walk on uneven surfaces. The final one there is the saddle joint, and you can see why it's called that from the setup here. If you it's probably upside down, really, this nature here, because that's the way in which the thumb is orientated. But if you look at it from a reverse perspective, you can see that the little legs, I guess, are coming over the saddle, and a little bit like a joystick setup where this thing can move in multiple directions. And what sets the thumb apart from the fingers, being a condyloid joint, the fingers can move in the directions I said before, but the thumb allows opposition, which means it can move in a joystick fashion, not only forward and back, but side to side and across to make opposition with the other fingers. So that's how we can achieve gripping and touching a thumb to a finger across the whole array of the hand. So those are the main classifications of joint that we come across in the human body. I want to talk a little bit more about exercise and articular cartilage health, because it is something that is affecting a lot of people, particularly as they age these days, is osteoarthritis and the wearing away of this cartilage. So how can exercise effectively aid this process? So with exercise, synovial fluid becomes less thick, less viscous, and if it's less thick and viscous, it makes it easier to get into the porous little holes that are found within the articular cartilage, and that allows the nutrient distribution right inside, and that allows the health and maintenance of that cartilage. Now, in order to make it thin enough to get in there, in order to compress the joint and get it to exchange these nutrients frequently, the exercise needs to be repetitive and it needs to be frequent. So that constitutes most types of exercise we do. If you're talking anything that involves running, then that is repetitive compression, obviously. If you're talking weight-based exercise, like weights in the gym, that's compression-based exercise as well. So your articular cartilage, while it might seem like a quite solid structure, and you're going to see it up close with a knee joint dissection that we'll be doing in a few days' time, And you'll actually be able to cut some of the cartilage, this articular cartilage, off the knee joint and have a look at it. And you'll see it looks quite dense, but under microscope you would actually see that it's very porous and there are these little holes that go right inside. It acts a bit like a sponge, and of course it's probably one of the most obvious of the use it or lose it physical structures in the human body. So if you don't use it, if you don't cause this compression and this nutrient distribution, then your body refuses to maintain it. And you lose it, you get a thinner layer, and then over your life cycle, as you start to age and our structures naturally start to wear down, you're going to pay for that. Alright, so the last two things we look at in this lecture here are two key variabilities of joint. You've got joint stability and you've got range of motion. And the two go hand in hand. You know, you've got to have an element of one to protect the joint. So stability is really important. Otherwise, the two bones migrate apart, and of course that leads to a dislocation or subluxation. But then you also need range of motion, because we perform a variety of exercises, and particularly in sport, we need to be able to achieve different positions where range of motion is paramount. If you can't get into those positions, then you're really limited in your athletic abilities. The downside of these two things is that while we need them in unison, that the production of one, or the increasing of one of these things, usually is at the expense of the other. So of course we've all seen, I'm sure, classic examples of ridiculous flexibility, and here's one example here. And we're always told to stretch, and we're always told to look after our body in that sense in terms of recovery, to make sure that we maintain a level of flexibility as we age, and that is vital information. But at the same time, if we get hyperflexible, then with hyperflexibility comes the risk of injury. So joint stability. These are the three things that essentially determine joint stability. Number one is your ligaments. Okay, so ligaments provide both the static stability, and the primary role is static stability. So when you're standing still, or when you're in posture and that kind of thing, then it is the joint ligaments that effectively do all the work in terms of stability. They're aided by muscles when it comes to dynamic stability. Okay, now ligaments themselves are very, very strong and flexible, and it takes an obscene amount of force to actually break a ligament and to tear a ligament. Again, you'll see this with the Cow dissection. We'll actually expose the ligaments in the knee joint, and we'll get to a point where the two bones, the femur and the tibia, are only held together by one ligament, the ACL, and then we'll have a crack at breaking it. And I can tell you, from end to end, if you're pulling from end to end, these ligaments are unbreakable effectively. You'd have to exert an obscene amount of force to actually get them to separate. However, they're not very resistant to torsion, which is a twisting-like force. So when the two bones not only try to separate but are twisted against each other, that's when we get an unraveling of the fibers and some tearing typically occurring. So ligaments attach the bones together effectively within the joint. If we strip all muscle, all fascia, all other connective tissue out of the body, and we're left with a skeleton with its ligaments attached, if I picked you up from the eye sockets, your entire skeleton should come with you. All of the bones would be attached via ligaments. They not only just attach things, they're actual receptors for the human body as well. There are sensory receptors found within these ligaments that send vital information to the nervous system about the position and range of motion of joints at any time. So in that sense, these, along with the joint capsule itself, with its sensory receptors in it, tell us where our body parts are. And that's how we know, without looking at our hands, that our hands are moving towards a ball to catch it. That's how we can close our eyes and touch ourselves on the nose with good accuracy, because we can feel where our body parts are in space without looking at them. And that feedback is provided by ligaments and joint capsules. However, and this is a big but, while ligaments are strong and flexible, they are not very elastic. They can only stretch to a point. Once they're overstretched, they may never regain their normal length. And this is something that not a lot of people know. So once you injure a ligament, sprain a ligament, it never really regains its normal length and strength. Okay, and once compromised, you are now at a higher risk of re-injuring those ligaments again and again, and we talked about that in injury rehab. And I asked people in the class, how many people have had a sprain, and a lot of hands went up, and how many people have re-sprained that joint multiple times and those hands stayed up. So that's where the stability-flexibility relationship comes into play. Again, that trade-off. If the ligaments can no longer do the job appropriately, then we've got to rely on something else to provide that stability. And the other thing that can provide that stability is muscles. So they aid static stability. Obviously we use muscles and stance as well. But when you're moving, these become the primary dynamic stabilizers of the joints. Okay, so if you think of the knee as a classic example, the quads, the hamstrings provide dynamic stability so that the two bones can't migrate away from each other. The ligaments are still resisting movement in the directions that we don't want it to happen, but they need added help because the amount of force that is going through the bones is now a lot higher. So if ligament function is impaired by injury, then strength training becomes a necessity to try and stabilize that joint and provide that additional static stability and dynamic stability. The downside of that, as just mentioned before, is that you make it more stable and then you lose some of your range of motion, which can compromise the way you lift and the way that you play your sport. So strength training is definitely something that should be built into any sports person's regime. And the old Arthur Lydiard days, if you remember him from training Peter Snell and these athletes, where runners ran and swimmers swam, and that's how they trained. Well, those days have changed somewhat, and a lot of runners, or definitely the high-level runners, are incorporating strengthening exercises into their regime as well as an injury prevention mechanism. The last thing that provides stability is the final connective tissue layer that wraps over the top of our tendons and our muscles, etc., and that is fascia, that connective tissue that wraps around muscles and attaches through and over the top of tendons to the bone itself. It gives another layer of added stability there, and some parts of the body have broad expanses of this fascia in the absence of muscle fibers. So a good way of thinking about this is if you're looking at a human body muscle diagram, you'll see places where there aren't any muscle fibers. One of those examples is in the lower back, where the lats end but don't directly attach to the pelvis at the back, and there's an expansive fascia over the top of that. The iliotibial tract runs off the base attachment or origin of the gluteus maximus and runs right down the outside of your thigh down to your knee, and it's just basically there as an integrity model that holds the muscles in place, okay, and that can also aid with stability as well. So there we see fascia as the outer layer on this muscle here, forming a sheath over the top, and it has its own connection over the top of the tendon into the bone. And here we see a picture of this fascia, and we see the iliotibial band. So you've got your glute here, your TFL, tensor fascia latae here, and then you have this fascia band in here. So you can see how that would provide integrity and keep the whole thing in place, particularly as we're moving. It acts like almost a very large ligament running from the top to the bottom here over. And you might be familiar with facial training techniques or recovery techniques or prevention techniques in the form of foam rolling. This is where we would typically use foam rolling to achieve a lengthening of this tissue if it became tight or too tight. Finally, some cartilage can be found inside some of the most loaded joints of the body. Classic example is in the knee, and we'll look at the knee as a wee case study to finish off, because of course that's what we're going to be cutting up in the days to come. So meniscus, or menisci, it's plural. Many people have heard of meniscus, or when you hear of cartilage damage in the knee, for example, that's generally what we're talking about. A pad of fibrocartilage that just sits between the two bones, providing an additional layer of cushioning. Okay. So here's an example of a knee joint here. Up the top here we have the femur, with its femoral condyles here covered in articular cartilage. And we have the tibia here, okay, and the tibia sort of fossa, which is this a sort of scooped out area in here. And this is why the knee is sometimes referred to as a condyloid joint, because it almost has a double ball and shallow double socket here that the two condyles here sit inside. Now, the thick wadge of connective tissue that you see here, here's the lateral meniscus you see, provides an extra layer of stability there for the heavily loaded knee. So it takes a lot of that impact off and stops this bone cracking against the bone on the bottom. And we have the medial meniscus on the other side here. When you cut open the knee, what we're going to do is try and isolate all of these ligaments here. So we'll actually be cutting away muscle and fascia and capsule, and we'll try to isolate the lateral ligament and the medial collateral ligament here. We'll try to find the ACL and the PCL. And we'll also end up separating these two bones, and you'll see beautiful examples of meniscus, which are C-shaped little discs that provide a little egg cup, effectively, for the condyle bones to sit in. Alright, so just to finish things off, we have the range of movement, which is the other thing that we're of course trying to develop. Now, as mentioned before, this is really limited and differentiated in different people by the shape of their sockets and the depth of things like the ball and socket joints, the condyloid joints, etc. So as you can see, this lady here has obviously developed her flexibility to fairly ridiculous levels there. So that's an indication that, again, she's able to go to that position because of the nature of her hip joint, taking it to bone-on-bone contact. Now, for me, I can tell you, not only would I not even get close to the splits, let alone taking my foot well beyond that, not only do I have muscular tension that might be stopping that, but of course my hip structure is never going to allow that to happen, meaning I probably have much deeper hip sockets than her. I'm sure many of you out there can sympathise with that. The main factors affecting the amount of range of movement that your joint can produce are, again, muscles and their tendons. So how tight and how short are your muscles and tendons? If they are very tight and short, then you're obviously not going to be able to stretch beyond that and take your joint through its entire range of motion. This is where preventative stretching and even aggressive stretching to some sense, when you actually do an applied flexibility program as part of your training, you're trying to get the most you can out of those structures there to allow at least your joint to go through its entire structural range of motion until we get near to bone-on-bone contact. So many of us have more flexibility in us, we just haven't allowed that to be developed because of the tightness of muscles and tendons, and I'm certainly one of those. Bulky tissue can have an effect on this as well. If you have an excessive amount of muscle, then it's going to prevent your body from getting into full range of motion positions. So you see this in heavily muscled bodybuilders that can no longer touch their fingers to their shoulders because their bicep is in the road, or they can't reach to the back seat of the car because the bulky tissue in between and surrounding the joints is preventing that movement. The other thing that will affect someone being able to achieve full range of motion is disease or conditions that are associated with the joint, and we'll look at a couple of them coming up. So the single most important factor in range of motion is the condition of your muscles and tendons. Got a wee case study here on YouTube, and this is a wee video of the shoulder joint that just shows the uniqueness, I guess, of the setup. And it starts with
the shoulder is an elegant piece of machinery. It has the greatest range of motion of any joint in the body. However, this large range of motion can also lead to shoulder joint problems. Understanding the different parts of the shoulder can help you understand how the shoulder works, how it can be injured, and how challenging recovery can be when the shoulder is injured.
So, we're not going to watch this entire video now. I encourage you to have a look at it on the full Prezi that's on the site. There are so many things around the shoulder joint. You can see them all being listed here on the side here. There's so many different components. And you can see that within the shoulder joint as well are these bony grooves and things at the scapula and underneath the clavicle, and things run in between all these gaps. So the shoulder with its range of motion takes the head of this humerus all the way up until it whacks effectively onto this acromion process right here. You can see that happening now. So you've got tendons running through here, you've got nerves running through here, you've got blood vessels, and of course if things aren't held in perfect alignment, those things could get jammed against the top of the bony surface that sits as the roof here. And of course that's going to cause inflammation and pain, and that's why the shoulder joint in particular is a common site of injury. Okay, now the muscles of the shoulder can help with this, and I'm just going to drag forward a wee bit here to give you a gist of it. It's going through the bony nature of the joint. We'll get to the point where we start laying down some muscles. So here's some biceps. Now they don't have a huge amount to do with the stability of the shoulder joint there, you can see, because they only attach here right at the top of the humerus or scapular attachment here and here. So we move through, we will look at some stabilizing muscles here, and here we see a couple. These are known as the rotator cuff. So see how they wrap both in front, anteriorly, and posteriorly to the shoulder joint there, forming a cuff that effectively stabilizes that humeral head so it doesn't migrate up, down, out, or back as we move. It holds it nice and snug against the socket, allowing a gliding sensation to go there and the full range of motion to be achieved. Now, if you were to injure those, or they were weak, they would allow the head of this to effectively migrate south often, okay, and that would cause separation between those two bones. Here's the delts, which we know are one of the key movement muscles as well. So all of these muscles here are providing stability because it's such a huge, hugely movable joint. It needs a great amount of musculature there to effectively stabilize it while it goes through its range of motion. Now, unfortunately, with lifestyle and the things that we often do during a day, like sit at a desk and use our mouse and have our shoulders rolling forward all the time, we can sometimes weaken particularly these posterior muscles here of the rotator cuff. And if they get weak, then we start to compensate when we lift our arm because we're very stable at this point. We use a lot of other musculature like our trapezius and our delts and those kind of things and overuse them in situations where they tire and we begin to lose form and function of the shoulder. And that can cause pain, that can cause inflammation, and that can cause issues that you're going to see quite a lot in the gym scenario there. We'll talk more about the injury ramifications of shoulders as we get through to muscle and that kind of thing there, but this gives you an idea of how muscles provide that stability around the shoulder joint. When we talk about the hips later, you'll see that there are actually 28 muscles effectively involved around the lumbo-pelvis hip region, and that's going to provide a hell of a lot more stability. And when you think of a shoulder versus a hip is far more stable because of the loading functions that it has. Bulky tissue, as I mentioned, can restrict flexibility, but is certainly not a given. As you can see in the picture here, this guy has ample muscle mass, obviously, but has maintained his flexibility. So it shows the importance, I guess, of maintaining flexibility while you build muscle. And this guy's obviously done both. To do this, of course, he would have to have some fairly hypermobile sort of bony structure there as well that allows him to get to those positions that most of us couldn't dream of getting to. Finally, disease or condition. Yeah, if something hurts, you don't want to use it. And if something hurts, it will generally hurt at the range of its movements. So, meaning that you'll be probably pretty comfortable with the limbs, for example, fairly close to your body, but the moment you take them to their outer ranges, then you lose a little bit of trust there as pain is usually imminent. That's often associated with muscular weakness or bone degradation. So we can see in the picture here, a spine being a classic example of osteoporosis, sort of eroding the bone in the bodies of the spine here and causing this unnatural sort of curvature here. And that is severely going to restrict range of motion there. The ability to even lift her head up, pull her shoulders back is now compromised. Pain, inflammation, muscular problems in the lower back, skeletal problems of osteoporosis can all be debilitating effects that can affect your range of motion. Okay, so that's effectively the joint presentation. The next step in the series is to have a look at one. So the joints are on order, coming in fresh. We'll get our scalpels out and we'll be tearing into these things and looking for the structures that we've just gone over. So don't be squeamish. It's something to look forward to. Your learning that you'll take out of it will be great. And once we finish this little section here, guys, and we've looked at bones and muscles, the next bones and joints, the next thing is to put the muscles on, and that's where we all want to get to. Thanks for your attention, and we'll see you again in class.